Hello and welcome back to another episode of Math with Son. Today we're going to be doing a double slit experiment, and this is coming from an AICE exam, specifically from May-June of 2024, and this is paper 2-2, number 6. Okay, so in this double slit experiment, we have wavelength, a light coming in of a single frequency, which matters because if it was multiple different frequencies, then it would be much harder for them to interfere with each other and create a interference pattern where you would have bright and dark spots on this semicircular shape. All right, and the question is asking if you have a specific wavelength and you know the great separation, determine the total number of bright spots that would be formed on the screen. Okay, so what's going to end up happening is as the light goes through here, you're going to have the brightest spot in the middle. And then as you spread out, as you go a little further, you might have another bright spot here, and then you might have another bright spot here, and you might have another bright spot there. Okay, and over and over again, you don't know exactly how many you're going to have yet, and it would definitely not exactly look like this, but this kind of helps me understand it too, to see that this is just multiple different bright spots, and then in between these two, we'd have dim spots. And that is happening from constructive and destructive interference between the two slit separations that we have. Okay? So you have two formulas at your disposal. You have one that is either d sine theta is equal to m wavelength. Other people may use a sine theta is equal to n wavelength or lambda, both of which are the exact same thing. It just depends on what letter you want to use. There's also d is equal to y max over L is equal to m wavelength. And all that does is transfer out the sine theta with the opposite and adjacent, which is really a trick because it's not really the opposite and the adjacent. In this case, I said it's the opposite and adjacent. It's replacing sine theta with opposite and adjacent, which is not what you should be doing. It's normally opposite and hypotenuse, but with small angles, you can get away with the opposite and adjacent. We're not going to use that one in this case. Okay, the reason why is because this is curved, the opposite and adjacent are going to be a little off. All right, so we got d sine theta is equal to m lambda, and we just need to figure out what angle can we put in and what wavelength and what slit separation. Well, we're given the wavelength, we're given the slit separation, 3.8 times 10 to the negative 6. The only thing we don't know is A, the angle that we should plug in, and B, what is the M, which is how many bright spots away are we from the middle. Okay, so the biggest angle that could be formed here is a 90-degree angle if you only focus on the top of the semicircle. And that's what we're going to do. We're going to focus on the top half, then we're going to focus on the bottom half. And here, this would represent M is equal to 0, this would represent M is equal to 1, this would represent M is equal to 2, so on and so forth. And we don't know how many of these we would be able to have going up the circle. But we do know that there are 90 degrees and that half a circle. So that's what we're going to do. We're going to put in that. So we got D, which is the slit separation. Some people use A. I like D a little bit more. 3.8 times 10 to the negative 6 sine of 90 is equal to M or N wavelength. And I'm looking for M. So I'm going to divide by wavelength because I would just do that. And I would divide by 520 nanometers, which nanometers is 10 to the negative 9. All right. So we type that in our calculator. And when you type that in your calculator, you end up with an M value of 7.3. Okay. So with my drawing, I got up to 1, 2, 3. Apparently, I could fit in a few more. I could fit in 7.3, which you cannot ever round up in this case, because if we kept going, let's say I could squeeze in a few more of these, I would end up with 7 right here, and then 7.3 would be at the 90, but I wouldn't get to 8 until after the screen ended. Okay, so really in this case, on the top half, we would have 7. All right, so I'm going to redraw that. On the top half, we would have 7 bright spots. Well, how many would we have on the bottom half then? We would have another 7. Okay, and many students think, okay, 7 on the top, 7 on the bottom, we got 14 total bright spots, and we'd be done. All right, we'd write 14, we'd be done, and we would be wrong. Even though this is a three-pointer, even though you were so close to the end, it's not 14, because the first and brightest spot in the middle does not count as an M value, and we have to add that 1 in the middle as well, which gives us a total of 15 bright fringes, okay? And that is how you solve that problem. Now, this problem keeps going a little bit, all right? It goes on and it states, the light is now replaced with red light, okay? So red light of a single frequency, which means it can still create that diffraction grating. State whether the frequency of the red light is greater than, less than, or the same as the frequency of the original light. Well, the original light had a wavelength, the OG, had an original of 520 nanometers. That was the wavelength. All right, and this is something you have to memorize, kind of like you have to remember nano is -9 and all the other things, and that is that red light has a frequency of, not frequency, it has a wavelength. I memorized the wavelengths. It has a wavelength of roughly, 620 to 750 nanometers. That is red light, all right? Which in both of those cases is bigger than 520, okay? So in both of those cases is bigger than 520, and if that is the case, if the wavelength is bigger, that means that the frequency would have to be smaller because wavelength has an inverse relationship to frequency. So if the wavelength goes up, frequency must go down. So that means that the frequency of the red light, which is what we're asking for, will be smaller or less than, okay? And I don't think we have to explain why, but you might need to. Let's see, it just says on the mark scheme, it just says frequency of red light will be smaller. So no matter what, this is kind of a freebie multiple choice question. You could guess, all right? Now we have to state and explain the effect of this change on the number of bright fringes. Well, the number of bright fringes, we might need to go back to our formula, which is d sine theta is equal to m wavelength. And if we solve for the m, which is what we did to figure out how many bright spots there are, you would divide by the wavelength, and that would go away. Now here, the d did not change. The slit separation did not change. The fact that we have to do sine of 90 doesn't change. We're dividing by the wavelength. If you divide by a bigger number, because the red wavelength is bigger, if you divide by a bigger number, what happens anytime you divide by a bigger number is you get a smaller result. And the result in this case is m, which is the number of bright fringes. So if we're dividing by a bigger number, we're going to have less bright fringes. So we will have less bright fringes, is the terminology they're using. Calculation not required. Okay, that's nice because maybe there's a chance that we don't actually have less. There's a chance that we fit in the full 7 on the top and the full 7 on the bottom, but it's not likely. Explain this, and that is because it's a 2-pointer, because the red wavelength is bigger. Okay? And everything else was held constant. Let's see, red wavelength is longer, so the number of less was that. So this would be worth 1 point, and that would be worth 1 point. Okay? And that's going to do it for this one. Until next time, stay positive, my friends, and I will see y'all later. Bye.